In this video, we are going to talk about uses of dimensions. Now, let's take the first one. We can use dimension to check the correctness of a formula. So we can use dimension to check the correctness of a formula, whether a formula is correct or not. If the dimensions of the left hand side in any equation and the right hand side are equal, then we can say that this equation is at least dimensionally correct. So the equation may be correct. And if the left hand side and right hand side is not the same, then the equation is not dimensionally correct. So the equation can never be correct. Now, a formula is given for a centrifugal force. Let's say F A is equals to mv square divided by r. Now, where m is mass, here m is mass, v is velocity, r is radius. Now, we want to check whether this formula is correct or not. To check whether a formula is correct or not, we will confirm the dimension of the left hand side and the dimension of the right hand side. So that is to your right hand and to your left hand. That is left hand side, right hand side. Now, right hand side or left hand side, we have force. Then the right hand side, we have mv square over r. Now, if we can confirm that the dimension of f left hand side is equal to dimension of right mv square over r, that is the same, then the formula is dimensionally correct. So the formula may be right. So let's say we know dimension of force already. That is ml t raised to power minus 2. You can watch the video on the first dimension and the second dimension before these uses. So you will see how we derive dimension of force. That is ml t raised to power minus 2. Now, to the right hand side, we have mv square over r. So what is m? M is mass is given, and v is velocity, and the dimension of mass is m. The dimension of velocity is lt raised to power minus 1. Velocity lt raised to power minus 1, everything square. So all this we've done it in the previous video, so you can go back and watch. Divided by r, I said r is a kind of length, so that means r will be in L. So this will be m L raised to power 2 t raised to power minus 2. That is, this 2 now will affect all this one. 1 times 2 will be 2, minus 1 times 2 will also be 2. So this will expand the brackets. So now divided by L. So now in this case, L can cancel out L. It will remain what? ml t raised to power minus 2. Now if you confirm this with this formula, you will see they are equal. That means the right hand side, Fe, is equal to the left, and the left hand side, Fe, the force, is equal to the right hand side mv square over r. That means the formula f is equals to mv square over r is dimensionally correct, meaning this formula may also be right because it's correct. So this is just illustration to how to use dimension to check the correctness of a formula. So now let's see example now. Example 1. Example 1. Check whether this equation may be correct or not. So we want to check if this formula is correct or not. Now f is force, v is velocity, t is time, and x is distance. Now p is pressure. Yeah, p is pressure. Now to check whether this is dimensionally correct, then we need to check if the left hand side, here the left hand side is pressure, while the right hand side is 3f v square divided by pi square t square x. So now let's confirm one by one. So I'm starting with the left hand side. The formula, that is pressure. What is the dimension for pressure? So we've already talked about pressure in the first video of dimension. We know that pressure is force over area, and we have already done the dimension for force. Dimension for force is ml t raised to power minus 2 divided by area is a kind of length. That is, area is equal to length times length. So area is equal to L square. That means the dimension of area is L square. So 1L will go here. So dimension of pressure is ml raised to power minus 1 t raised to power minus 2. This is m over L. So that L will carry power minus 1. So that means this is dimension of pressure. So let's do the right hand side also to confirm. So the right hand side. Right hand side. We have 3fv square divided by pi square t square x. Now we've already know that for any constant, 3 is ordinary number, so the dimension is 1, as in this is ordinary number, its dimension is 1. F is force, the dimension is ml t raised to power minus 2. The dimension of velocity lt raised to power minus 1, then everything raised to power 2 divided by the dimension of pi. We already know that pi 2 is dimensionless in video 1, so that is 1 square. Dimension of time is t, that will be t square. Dimension of x is L, because s is distance, and distance is also a kind of length. So if you watch the first video, you can watch the first video to understand all this better. So here we are just solving, we are doing the uses of dimension to check the correctness of a formula. So now this will be m lt raised to power minus 2 times l raised to power 2 t raised to power minus 2, meaning the power here is 1. That will be 1 times 2. The number outside will multiply the one inside. Everything over t square times L. Here, 1L will cancel out. So we'll have ml square, because we have 1L here and another 1L. That is ml square t raised to power minus 4. That is minus 2 minus 2. That is minus 4. Then this one, you can take it up as the power. That will be minus 2. Because law of indices, t raised to power minus 4 divided by t raised to power 2. The law states that divide, you subtract the power. So that will be t raised to power minus 6 together. So that means the dimension is ml square t raised to power minus 6. Now confirm the two results. The dimension for the left hand side is this, while the dimension of the right hand side is this. They don't have the same value, so that means this formula is not dimensionally correct. So the formula can never be right. So that means the formula P, pressure, is equals to 3F V square divided by pi square T square X is not dimensionally correct. So the formula is not correct. So it means it cannot be correct. So if we now have, or let's say another example. So let's say we have, equation of motion V is equals to U plus 80. So let's test if this is dimensionally correct. Now the left hand side here, left hand side is velocity. And what is the dimension of velocity? This left hand side, velocity is displacement over time, and displacement is a kind of length, so it will be L, time is t. That means dimension of velocity is lt raised to power minus 1. We've done this in the first video also. Now let's say the right hand side. For the right hand side, we have u plus 18. Now u is velocity. We have known the u is also velocity, that is initial velocity, and the dimension for u is lt raised to power minus 1 plus. Now I can conclude on this that before these two can be added together, they must have the same dimension. So but let's do it to the end. So dimension of acceleration is lt raised to power minus 2 times time. Again, dimension of time is t. So this will becomes lt raised to power minus 1 plus lt raised to power minus 1, because the power here is 1 and we know that minus 2 plus 1, so this will be minus 1. We're using this is. Now this is the same thing as 2 lt raised to power minus 1. This is 1 lt raised to power minus 1 plus another lt raised to power minus 1. So we have 2 of it. And as ordinary number is dimensionless, 2 will be dimensionless. So that means this will be lt raised to power minus 1. So if you check now, the dimension of the left hand side is equal to the dimension of the right hand side. That means this formula is dimensionally correct, so the formula may be correct. So that's it. So now let's say another one. You may not add these two together if you like, but you will know that since the dimension of this is lt raised to power minus 1, here too is lt raised to power minus 1, that means their results must also be lt raised to power minus 1, which is true. So that means it's dimensionally correct. So reason is that if this is minus, so you won't get 0 there. So you can use the techniques. If you add the two quantity, then the units must be the same as this, and it's the same. So now let's see another example. Now let us confirm if s equals to ut plus half at squared is also dimensionally correct. Now if you look at the right hand side and the left hand side, the left hand side is displacement and is a kind of length, so the dimension is L. Now let's confirm the right hand side. For the right hand side, we have ut plus half at squared. So that means u is velocity, and we have found the dimension is lt raised to power minus 1. You can check the first video for all this beginning. Times time is time, that is t. So that is u is lt raised to power minus 1. T is capital T, and that will be raised to power 1 plus half acceleration is lt raised to power minus 2 times t raised to power 2. So this will be L t raised to power 0, because minus 1 plus 1 is 0. If you use law of indices, plus half is a number, so it's dimensionless. So again, this will be lt raised to power 0 minus 2 plus 2 if you multiply using the law of indices. That means we now have L, because anything raised to power 0 is 1. So that will be L plus L, as in this one too, everything is 1. So since we are adding length plus length, their third result must also be in length. That is, this is in length. We have proved that this is length, this is also length. That means if you are adding the two lengths, you must get length in the third result. Just like 5 meter plus 4 meter, it must give you 9 meter. So meter, meter, meter. Or L plus L is 2L. 2 is dimensionless, so that will be L, like that. That means the formula S equals to ut plus half at squared is dimensionally correct. So the formula may be correct. Now we can also use dimension to derive a new formula roughly. So we can use dimension, that is, we can derive, that is number 2 usage, that is number 2 uses of dimension. We can derive a new formula roughly. So we can derive a new formula roughly. So let's see example here on how we can use dimension to derive a new formula roughly. So example. So another example. Derive the formula of time period of simple pendulum. If time period of a simple pendulum depends on mass, length, and gravitational acceleration. Now, to use dimension to derive a new formula, so we can say for this kind of question, we can say that expression of t, that is period, should be in this form. So t should be in this form. T is equals to some number T is equal to some number m raised to power a, that is mass, L raised to power b, and L raised to power a, m raised to power a, L raised to power b, and g raised to power c. So meaning this formula are dependent. So we can also determine whether all these quantity mentioned here are dependent. You can determine whether they are dependent. Maybe we should do that roughly. That is, before we can say this expression is this, because since they are dependent, then we can have it as m raised to power a, L raised to power b, and g raised to power c. We can have it that way. So we'll later show why an expression or a term can be dependent, so that we'll have them separately. So now, and again, g is gravitational constant, so it depends on other quantity. So in this question now, this is the first thing we write. That is, we want to derive a formula that will depend on mass, length, and gravitational acceleration of a simple pendulum. Now, t is the period. This is some number, then mass, length, and the gravitational acceleration. Just study the concept. So now, let me bring it up so we can derive. So now, let's say, let me bring it up. So now, to proceed, we already know that mass is capital M, length is L, and G is acceleration, gravitational acceleration. We know all the dimension already. So that means T is equal to some number. That some number now is dimensionless. So that will be 1. We say any number is dimensionless. So M will be raised to power A, L is raised to power B, G is gravitational acceleration, and dimension for acceleration is LT raised to power minus 2, then raised to power C. Since period is T, that means it's time is also T like that. So we can say M raised to power 0, L raised to power 0, T raised to power 1. Anything raised to power 0 is 1. That means all this expression is still the same as T. Is equal to M raised to power A, L raised to power B. This C will affect everything in the bracket. That will be times L raised to power C, C raised to power minus 2C. Because this power will multiply everything outside there. Now, we can easily say this is M raised to power 0, L raised to power 0, C raised to power 1. Now, which one is the same here? M raised to power A times, we have LL, so we can add the power. That will be L raised to power B plus C times C raised to power minus 2C. Now, if we compare both sides, you will notice now that M will go with M. That means the power on M is A. It will be equal to 0. That means A is equal to 0. The power on L is 0. And power on L here is B. You can also say B plus C is equal to 0. From here we can find B. B will be equal to minus C. Collect the like terms. Now the power on T is minus 2 here, and the power it will be minus 2C here. The power on T here is 1. That means minus 2C is equal to 1. then c is equals to minus 1 over 2. Now if c is minus 1 over 2, we can put it here to find b. Since b is equals to minus c, then b is equals to minus, so c is minus 1 over 2. So minus times minus plus, so that will be 1 over 2. So we know a now to be 0, b to be 1 over 2, c to be minus 1 over 2. So now we can come back to our period. So that means t is equals to some numbers. So let's say t equals some number, then m raised to power a. We already know our m, but a is 0. Then l raised to power b, that is b is 1 over 2, and t raised to g raised to power g raised to power minus half. As in, if we come back to this place, m is raised to power 0, b is raised to power half, c is minus half, because we already know all the values here. Now t is equals to some number, m, anything raised to power 0 is 1. That means the m is 1. Then this is l raised to power half divided by g raised to power half. You know that the g is raised to power minus half. That means g raised to power minus half is equals to 1 over g raised to power half. So it will come under the L. Now if you look at this two, half is common here. That means period t is equals to some number L over g raised to power half, meaning this half here and this half here will be common. You take one out, then t is equals to some number square root of L over g. Now because power half is the same thing as square root, so if you look at this final answer, so this is our period. That means we have used dimension to derive roughly the formula of period in a simple pendulum. So now if you look at our formula, our final answer, the quantity that I represent as some number here can be found experimentally. So measure the length of a pendulum and oscillate it, then find its time period by stopwatch. So then you can easily find L. So suppose L, let's say we want to get this experimentally, this some number, so that you can understand. But this is the answer for the question. That is, we have derived a formula. So I just want to explain that some number, so we can get that some number experimentally. So to get the sum number experimentally, we can, let us assume L is equals to 2. And so let's assume L is 1 meter in the laboratory. Then if L is 1, we get 2, we get T to be equals to 2 seconds. So if you substitute, meaning in the laboratory if the length is 1, the time is 2. So if you put it in the formula, you have 2 equals to some number. some number roots 1 over g is constant, that is 9.8. So that is acceleration due to gravity. So some number is equals to 2 divided by square root of 1 over 9.8. So if you press calculator direct, so some number is equals to 6.28, which is approximately 2 pi. So that means the sum number experimentally can give us 2 pi if we work it out in the laboratory using the lengths L to be 1 and T to be 2, like that, 2 seconds. So now let's see another example. So we can also use it again to get other formula. So another example, if velocity v, force F and time t are chosen as fundamental quantities, express I mass, I energy in terms of V, F and T. So let's start with the first one, I. We want to express the mass in terms of V, F and T. So V, F and T are dependent. I will still show you how we can determine or how we can prove that a certain quantities are dependent. So now mass, we want to express mass in terms of Vf and T. So mass is equals to, we can say some number, then V will be raised to power A, F will be raised to power B, and T will be raised to power C. So that means we can go further. Mass is m already, so we can say m L raised to power 0, T raised to power 0 to write it in terms of mlt. So some number, that some number will be 1. It will be dimensionless. So v is velocity, that will be L T raised to power minus 1, then raised to power A. F is a force, and we know what a force, the dimension of force is. Dimension of force is ml T raised to power minus 2, then raised to power B. T is time, then is raised to power C. You know it's power 1. So now this is m L raised to power 0, T raised to power 0 equals L raised to power A, T raised to power minus A. Meaning this is power 1. That will be 1 times A, 1A. And again, minus 1 times A, that is minus A. Then times m raised to power B, L raised to power B, T raised to power minus 2B. That is, this B now, we have fed all the powers inside. We will multiply. Then times T raised to power C. Now if you equate all the powers, so m L raised to power 0, T raised to power 0. So I have L raised to power A times L raised to power B. In indices, it will be L raised to power A plus B. Combine these two L using law of indices. So times, now let's see m. M is T raised to power B, only one m. Then T raised to power minus A, and T raised to power minus 2B, and T raised to power C. Combine everything, take one and add the power. T raised to power minus A minus 2B plus C. So that's how we add down. So we can compare both sides. So if we compare both sides, this m is power 1 here, The power on m is 1 here. The power on m is b. Yeah. So that means if you equate b is 1, if you equate also for L, a plus b is 0. So that means the power there, a plus b is 0. That means power on L is a plus b here. It is 0. Yeah. So that means if we collect like terms, a will be equals to minus b. And we know b as 1 before. So a is equals to minus 1. So now equate the last power. That means minus a minus 2b plus c is equals to 0. So c is equals to a plus 2b. Collect like terms. So c is equals to, what is a? Minus 1. We know it already. Plus 2b. What is b? B is 1. So that means c is equals to minus 1 plus 2. So c is equals to 1. That means we have known our a, we have known our b, we have also known our c. So if you know ABC, so go back to your formula. M is equals to some number V raised to power A, F raised to power B, T raised to power C. That means M is equals to some number V. A is what? We know A as minus 1. F, we know B as 1. So we know B as 1. And t raised to power c, we know c as 1 also. So that means this is the sum number is constant, so I may remove it. That means the dimension of m in terms of v is v raised to power minus 1, f raised to power 1, t raised to power 1. So that is the dimension of m using the information given in the question. Now, what of dimension of energy? The same way we did for for mass, we can also do it for energy. As we say, m is equals to some number, so I'm going to say E, energy, is equals to some number. So now let's say that one. So I'll change the m to E, still the same way. So I now, so the m will turn to energy the same way. So now, but energy is work done. Yeah. So energy is a kind of work. So that means, and we've already said that work done is what? Force times distance. And force is ml t raised to power minus 2. Distance is a kind of length. So work done is ml square t raised to power minus 2. So that means we need to equate the two together now. So that means L will carry 2. Yeah. So that is energy. So it's work done. So ml square t raised to power minus 2. So now let's equate that one. So energy can be ml square t raised to power minus 2. So that will be energy. So now is equals to some number, that will be 1. So which is equals to v 1 brackets v, that is lt raised to power minus 1 raised to power a, the same way as the previous one. mlt raised to power minus 2, then raised to power b, then t raised to power c. So this will becomes L squared t raised to the power minus 2 is equals to L raised to the power a t raised to the power minus a, similar to the previous example, m raised to the power b L raised to the power b t raised to the power minus 2b times t raised to the power c. So m L squared t raised to the power minus 2 equals L raised to the power a plus b times t raised to the power minus a minus 2b plus c times m raised to the power b the same way. So now let's start the equating again. The power on m here is 1, the power on m here is b, so b is equals to 1. Again, the power on L here is a plus b, the power on L here is 2. That means a plus b is equals to a plus b is equals to 2. So that means this will be 2. And we know b as 1. So that means a is equals to 2 minus b. That means a is equals to 2 minus 1. So we can easily know that a is also 1. That means a is 1, b is 1. So to find c, we can equate the t. That means minus a minus 2b plus c is equals to minus 2. The power on t will be equals to the power on t here. So if we equate now, this will become c is equals to minus 2 plus a plus 2b. So c is equals to minus 2 plus 1 plus 2 times 1. So that means c is equals to minus 2 plus 1 plus 2. So c is equals to 1. That means a is 1, b is 1, c is 1. So now go back to your energy. So energy is from here now. Energy is some number which is constant. Then v raised to power a is 1. F raised to power b is 1. T raised to power c is 1. So that's the answer for that one. Now number 3. We can also use dimension to find out the units of a physical quantity. We can use, that means number 3. We are still on uses of dimension. We can use dimension to find out uh, the units of a physical quantity. You can use dimension to find out the units of a physical quantity. So for example, force is equals to m raised to power 1, L raised to power 1, T raised to power 2. That means the dimension of force is this. We can now get the units of force from this dimension. So let's say now, as unit of mass is in kilogram, unit of length is in meter. So mass in kilogram, length in meter, and unit of time is in second. So unit of force can be written as F now can be kilogram raised to power 1. So unit of mass raised to power 1. Length, that is m raised to power 1, that is meter. Time, s raised to power minus 2. So that means the unit of force is equals to kilogram meter per second square. That means this is the unit of force. So we can also use dimension to find out units. So that means again in mks, that is kilogram, mass, mks system, and also the cgs system. if it is CGS system, that is centimeter, gram and second. So the MKS is mass, kilogram and second. So in CGS, this one is MKS, mass, kilogram, second. So if it is in CGS, force will be gram, centimeter and second. So that means CGS, gram, centimeter and second. It depends on your answer. So that means per second. Okay, so it's like per second square rather. So that means that is how we can use dimension to find out the units of a physical quantity. So let's see what we can talk about again. So now let us see limitation of dimension. Now let's see limitation of dimension. So what is the limitation of dimension? Now number one limitation, you can jot this one down. That is limitations of dimension. And let me put it like limitation of dimensional analysis. Limitation of dimensional analysis. Number one, you can jot. Now, from the dimensional analysis we have been doing so far, we got something like this. Like T is some number square root of L over G. We got this at a point. That is period of a simple pendulum. We said is some number root L over G. Now the expression, this some number we don't know. The expression can be 2 roots L over G. The expression can be T is equals to root L over G sine anything. The expression can be T is equals to root 50 root L over G, meaning this some number can be any number, as in we don't know what we can have there. So dimensional analysis now. So the limitation, number one limitation, dimensional analysis doesn't give us information about the some number. That means you won't know which number is there. So dimensional analysis doesn't give us information about the some number. So that means the dimensional constant. So dimensional analysis does not tell us about the dimensional constant, which I represent as some number. So number one limitation, get it again. The dimensional analysis doesn't give us information about the dimensional constants. So put it that way. Number two, this method is useful only when a physical quantity depends on other quantity by multiplication and power relation. Number two now, so you can backward the video. I said this method is useful only when a physical quantity depends on other quantities by multiplication and power relation. That is, since we have been proving, as in we have been deriving a formula for dimensional analysis, we are doing something like this, that f, let's say f depend on x, y and z, a, b and c. That means these three, x, y and z, are dependent. That's why we say this method is useful only when a physical quantity depends on other. So by multiplication of power, and that's why we are using it this way. Then number three, it fails if a physical quantity depends on some or difference of two quantities. So a physical quantity depends on some, like let's say f is x plus y minus z, then this method will fail. And again, we cannot use we cannot get this relation direct. S is equals to ut plus half at square. We can't get it direct using using the dimensional analysis. That's another limitation. So number 4, this method will not work if a quantity depends on another quantity as sine or cosine, logarithm or exponential relation. This method works only if the dependence is by power function, as we are multiplying by power since to get our derivation. We equate the powers MLT, hence we get only 3 equations. So we can have only 3 variables, only 3 dependent quantity. So that's what we can only have in using dimensional analysis, since we are using MLT. So that means we can only get 3 quantity. That is another limitation. That is, the limitation can only allow us to use MLT to so that we can have only 3 variables. So now, another thing that I said I will talk about is how to know if a quantity are dependent. So let me just use that one to end this video, so we can do error analysis in another video. So let me say, can pressure, let me ask as a question, let's say, can pressure P, density, can pressure P, density, and velocity V be taken be taken as fundamental quantity? So the question is, can pressure, density, and velocity be taken as fundamental quantity? We can prove it. Normally we know it cannot, because velocity is displacement over time. It depends on other quantity, so it will fail. But let's show it mathematically. So P, density, and pressure, density, and velocity are not independent. That is, they can be related as P is equals to density V square. So we can relate it as this, that is P density V square. So they cannot be taken as fundamental variable. So to check now whether P, density, and V are dependent or not, we can use the following. So we can say P, pressure. So what is the dimension for pressure? We have proved it. That is ml raised to power minus 1 T raised to power minus 2. That is force over area. That is m raised to power 1. Also, density, we have shown that one too. That is m raised to power 1 L raised to power minus 3, then T raised to power 0. Density is mass over volume. That is m over mass over volume is v cube. That is L cube. If you check the first video, so you will understand all this. So that is density. Now the last one is velocity. That is LT raised to power minus 1. M is not there, so that will be T raised to power minus 1. Check the video, you see this also. So now we can check the determinant of their powers. So let's check the determinant of their powers. So now we have 1 minus 1 2 for the pressure. That is 1 minus 1 minus 2. Also we have 1 minus 3 0 for the density. 1 minus 3 0. So we also have 0 1 minus 1 for the velocity. So that will be 0 1 minus 1. So if you check the definition, what I gave you on determinants, I found the determinant of 3 by 3 matrix. So I did it this way, like 1 minus 1 1 minus 1 minus 2, 1 minus 3, 0, 0, 1 minus 1. Do as if you write it again, but write the first one. Check my video on determinants so you will understand this part better. So minus 3, 0, 1. So take a 3, 3 this way. That means the determinant here is 0 times minus 3 times this 0 plus 0. This times this again. Then the last one, that is plus 1 minus. Now take a 3, 3 this way also. This is 3 plus 0 minus 2. So that means this is 1 minus 1, which is 0. Now, since the determinant is 0, so these 3 terms are dependent. That's how we can prove it. So thank you. We'll continue with dimensional error analysis. Watch my video on determinants. You will understand these parts better. Thank you.